Welcome back to the final part of Lecture 13. In this part of this lecture, we're going to look at how we might evaluate v subscript s, that slip velocity that we've been talking about. I'm going to present two ways in which that can be done, and both of these ways fundamentally rely on the fact that we're going to break our flow down into two components, a slip component and a bulk flow component. So let's start by talking about that. Up until this point, we've said that we may have slip at a wall, and that may be characterised by a slip velocity v subscript little s. What's happening in the remainder of the flow is hopefully described by one of our constitutive equations. The profile I've drawn here is viscoplastic, and it may be a Herschel-Bulkley, it may be a Bingham. If I add these two components of flow together, I will get a representation of the real flow that's happening within my system. Now, if we think about that, we can write down the volumetric flow rate expressions that correspond to it. Q here is the total volumetric flow, written in pink. The contribution from wall slip I've written as pi r squared Vs. Okay, so r is our pipe radius, this assumes a pipe flow. Vs is our slip velocity, and the reason why I've written it as r is that we know that the slip layer occurs very close to the wall and is very thin. So the radius of the zone that is flowing compared to the radius of the pipe are essentially the same thing. I've written the bulk flow component in a form that we introduced when we were talking about capillary rheometry. The idea was to find an expression for volumetric flow rate that didn't presuppose a rheological response. And if you recall our discussion on the Rabinovich correction, this is the form that we used just before we inserted it into Leibniz's rule and got a rearrangement via which we could analyse experimental data. Now, let's think about the wall slip part of this expression, Vs. Vs, we saw in a previous part of this lecture, could be related to the wall shear stress and a constant, a material constant, via something called the Navier slip law. So I've used the Navier slip law for the wall slip component of the volumetric flow and simply rewritten the equation in terms of that. So now we have beta n, our Navier slip constant, and tau w, our wall shear stress. So here on the board in front of you is a reminder of the equation that we've just developed. And what I'm going to do is just manipulate it subtly. So the first manipulation I want to do is divide through by terms involving wall shear stress and pi r cubed. That allows me to write beta n over r as a term in this equation. Now, let's make an assumption. Let's assume that the experiments we do are at very low flow rates. Under these circumstances, we hopefully haven't exceeded our yield stress of the material, but we have exceeded a stress at the wall that causes slip to occur. So, for these deformations, gamma dot will be 0, hence our integral in blue will be 0, and we've got remaining two groups that we can plot against each other in order to reveal a value of beta n. Another thing that we can do is we can use effectively the same approach, but just rewrite the equations a little bit differently. If we think about Q, written in pink, and divide by pi r squared, that gives us our mean velocity, v subscript m. If we further divide through by r, then we get v mean over r, which is a measure of shear rate. So my shear rate, gamma dot, beta n tau w over r plus the integral, which goes down to 0 if tau y has not been exceeded. And what we do is we plot gamma dot against tau w. This involves multiple experiments using capillaries of different radii, so we've got a large data set from which to get a reasonable estimation of what the slip parameter beta actually is. So, a few key points. We can analyse slip by breaking a flow down into the bulk flow and the slip flow and adding them together to equal the total flow. We can use that approach with volumetric flow rates, and we can use the Rabinovich result to set to 0 if our yield stress hasn't been exceeded. Multiple experiments are required at different radii in order to get a decent enough experimental data set, however, for this approach.